Good morning, good afternoon, good evening, everyone. Welcome to iCANX Talks, Connecting the World and the Universe. Today, I'm your moderator, Professor Martin Thu, coming to you from North Carolina State University in the Eastern United States. For this month, we are very privileged to have two talented professors originally from Africa, Abraham Badu-Tawiah and Abdoulaye Ndao. And then next week, we'll have the talented, amazing Francesco Starachi, followed by Louis Mazen. And then we will have Rebecca Kramer from Yale talking about liquid metals. Today, I'll be joined by a very wide panel because today we are highlighting Africa science and technology. I will be joined by Professor Ruth Wanjao, Professor Dennis Karanger, Professor Edwin Fotang, and a Kenyan politician, Alice Nganga, and then Professor Femi Onjabati. You asked the question, why Africa? And we want to highlight Africa because it's rich in talent and resources. For example, from landmass alone, Africa is 30.4 kilometers squared, which means, for comparison, Africa is about more than 3 times the size of US, more than 3 times the size of China, and almost twice the size of Russia. But if you look at the narrative of Africa across the world from cartography, from maps, you realize that because of the projection, Africa looks much smaller than it is. The global north is overemphasized, while Africa looks like a much smaller country. Yet if you compare Greenland to the landmass in Africa, Greenland here is the size of the country of Congo. And if you take that even further, you can see from a landmass alone how much you can fit into the continent of Africa. And it's not just from the landmass. Africa has one of the youngest world's population with an average age of about 17 years, which means that the future of the world is resting in Africa. But the scientists in this continent do not have the same amount of resource. There is asymmetry in resource. So African scientists must think outside the box to carry out competitive and relevant research. And they have to train in ways that the rest of the world did not get trained, which means there's a lot of creativity. And even today, you see the kind of papers coming out of Africa, they're not limited. We have papers like this from Botswana in Nature Material. We have a paper like this from the island nation of Mauritius, Luxembourg, in Accounts of Material Research. So the work is high quality. And today we will highlight this. And we want to share with the world that Africa is rich in talent, and these African scientists are doing way much more than they get credit for. And for today, we are very, very privileged to have our first speaker, Professor Abdoulaye Ndao. He's a great son of the continent. He got his PhD from France and then moved across the Atlantic all the way to California, where he was a postdoc in UC San Diego, and then UC Berkeley. And after that, after working with the Boubacar Kanté in Berkeley, he moved to Boston University, where he's an assistant professor. And Abdoulaye has way too many awards for me to go through all of them, but I want to highlight a few of them. More recently, he has been named Beckman Young Investigator Awardee. He has been named for his teaching. He has a Best Teaching Award from Boston University, Best Service Award from Boston University. He has funding from Kavri Foundation, which is very, very prestigious, and also is a Scialog Fellow. Among many, many other awards, Abdoulaye, I don't want to steal your star. I would like to hand it over to you. Please share your slides and take over.
Thank you, Martin, for the kind introduction, and thank you for giving me the opportunities to present my work today. So again, my name is Abdoulaye Ndao, Assistant Professor at Boston University in Electrical and Computer Engineering Department. So today I would like to talk about symmetry and topology in photonic nanostructure. So as we all know, in the recent years, the demand of miniaturization and integration is really a great interest, especially the devices that we are using in our daily life, such as like GPS, cell phone, and so on. So as an example here, I would like to take the new cell phone as an example, you can see clearly here in a very tiny space you have multiple functions, which means that in order to satisfy such high demand, new integrated devices must be compact, highly efficient, multi-frequency band operation, and so on. So in this perspective, we propose a new type of laser that we call topological laser that can have an arbitrary shape. What does this mean? This means that you can pack them densely on chip without losing the functionalities. It is one-way propagation, which means that you don't need any additional component to avoid backscattering of the light in the system. The second part of my talk is exceptional point sensor, where we show for the first time that you can have exceptional point at sub-wavelength scale. And we can use such exceptional point to demonstrate almost 300 times better than the state of the art in terms of detection. And the third part will be dedicated to broadband achromatic metal lens, where we show for the first time that we can have a broadband achromatic metal lens that can go from visible to the IR with a very high efficiency. So what is topological insulator? So imagine you have an insulator material for given energy band, condition band, valence band, and band gap, and you take free electrons inside the bulk material. They cannot propagate in any direction because you are in a gap region. However, if you take bulk material and topological material and you apply a magnetic field, you can see that you can have some as the electron circulated in the same direction, but also with the same cyclotron frequency. In this case also, for given energy band, condition band, valence band, and band gap, it will not propagate in any direction because of vector cancellation. So now, if you look at right at the boundary here, what you can see is you can see some semicircle. What does this mean? This means that if you take free electrons right at the boundary, they will start to follow the trajectory and propagate in forward direction regardless of the shape of the boundary. In this case, which are quite similar to the quantum Hall effect, we use external magnetic field. Again, there are many other cases that don't require any external magnetic field, but are based on spin Hall effect. For example, when it is spin up, they will propagate in forward direction. When it is spin down, they will propagate in backward direction. All the history I just mentioned here and many other stories show the robustness of topological insulator. But it was demonstrated that under specific conditions, under specific characteristics, such as breaking time reverse asymmetry, breaking spatial symmetry, or creating artificial gauge field, some of those fermionic systems can be transferred to bosonic system like photons. This work was awarded by a Nobel Prize in 2016. And topological insulator was used in different platforms, in different frequency range, from acoustic to microwave, in terahertz, or in optics, using as a ring resonator or a spiral structure to create artificial gauge field. All this work I just mentioned here and many other work in the literature try to show the robustness of topological insulator. But the questions that we ask ourselves, can we use such a topological insulator to make real devices? And the response to that question came in 2017 in Alberto Amos' group, where they used the HSS model to show a first D topological laser. And later on in our group, we proposed in the same year a new type of topological laser that can have arbitrary shape, as I mentioned before. It is one-way propagation, which means that you don't need an isolator. And we use a magnetic material to break the time reverse asymmetry. And 1 year later, another laser was also proposed using a ring resonator and an artificial gauge field to generate topological laser. So today, I would like to focus on the topological laser using magnetic materials that we develop and how we develop such system. So this is the platform that we use. And in this platform, we have two types of photonic crystal. We have one photonic crystal, which is inside the cavities, which is the star-shaped photonic crystal with a triangle lattice that we designed to be topological, non-trivial photonic crystal, and the air-hole-shaped photonic crystal, which is outside the cavity. It is designed to be trivial photonic crystal. And both photonic crystals that we have here are made in GASP, which is the indium gallium arsenide material, which is the gain material, and that has the highest gain around 1.55. Since the goal of this work is to have lasing around 1.55. And we combine those material are all bound in a magnetic material that we call yttrium iron garnet in order to break the time reverse asymmetry. How the system works is you uniformly pump the whole structure with processing external magnetic field, and we will have an edge state that will couple out, and in this waveguide that correspond to removing one line of the trivial photonic crystal. So how we design such photonic crystal? We first start with the air-hole-shaped photonic crystal, which is the photonic crystal outside the cavity. And we look at here the band diagram of this photonic crystal, which is the air-hole shape with the triangle lattice. And you can see we have a very huge band gap. And when we calculate the chair number of the mode below this band gap, you can see that the value is equal to 0, which means that we have a trivial photonic crystal. And the next step, of course, is to design the star-shaped photonic crystal with the square lattice, which is inside the cavities. And in this case, also, you see here, when we apply magnetic field, we have a very narrow band gap that is open. And when we calculate the chair number of those modes below this band gap, it is equal to 1, which is non-zero, which shows that we have a non-trivial photonic crystal. Again, the goal is to have lasing around 1.55. So what we did is we choose the geometrical parameters of both photonic crystal in order to have their band gap overlapping around 1.55, since the lasing plan is to have it at 1.55. So now the next step consists of how to excite such mode. So what we did here, you can see it on the right with this yellow star. We put the two photonic crystals next to each other, and right at the boundary, we put a point source. And what we did is we applied magnetic field upward, as seen here, and you can see that we have forward propagation of the light. And when we flip the sign of the magnetic field, the light will propagate in a backward. So this shows that we can use a hybrid system combining different material and two types of cavities to show we can have edge state of a photonic crystal, which is one-way propagation. Now the next step is how to implement such photonic crystal. So in order to fabricate this system, we use three different main of method, which is e-beam lithography to define the shape, etching, and bonding in magnetic material using an interlayer. And you can see in the ACM image here that the star-shaped photonic crystal, the air-hole-shaped photonic crystal, and even the waveguide to couple light out are very well defined. The cavity is also very well defined, which shows the quality of the fabrication of our devices. So after successfully fabricating these devices, the next step consists of measuring the output power. So what we did first is we uniformly pump the whole structure without processing any external magnetic field. And you can clearly see here there is no edge state. And the next step consists of applying magnetic field. We can clearly see edge state. And to be sure such edge state that we are seeing here correspond to the lasing action, what we did is we look at the pump power as function of our output power. And you can clearly see here we can go from spontaneous emission to the lasing action. Again, I mentioned at the beginning of my introduction, regardless of the shape of the boundary, we can have edge state, but we also can have unidirectional lasing. So how we can characterize the system and show that it is unidirectional. So there is two ways of doing it. The first one consists of having two lenses fibers coupling to the waveguide, because the waveguide is evanescently coupling to the cavities to outcouple the light. So what method can we use is to have two lenses fiber at the edge of the waveguide and look at the ratio, which will tell us if it's unidirectional or no. But this method is very challenging because controlling the coupling coefficient on the both sides of the waveguide is very challenging. So we use the second method, which consists of using only one edge of the waveguide that we couple with the lenses fiber. And in this case, what we will do is we will just flip the sign of the magnetic field. And you can clearly see here, by having the magnetic field upward, we have lasing in blue. And when we change the sign of the magnetic field, we don't have lasing, which shows that we have a one-way unidirectional lasing. And it is one-way propagation with the isolation almost 10 dB. So coming back to the introduction, regardless of the shape of the cavities, we should be able to see the same behavior, which means that it should lace. So by choosing the same dimension, same way of designing it, and same fabrication, we change just the cavity shape. And you can clearly see that by changing the cavity shape, you can have, when you apply magnetic field, you have edge state and you have isolation almost 11 dB. This is another second cavities that we design. It is behaving the same edge state. You have lasing and no lasing by just flipping the sign of the magnetic field. Again, I mentioned you can shrink the shape of the laser without losing any functionalities. So the idea is to use arbitrary shape of the structure. So again, the design was done in the same way, and the dimensions that we use on all those lasers are exactly the same. The only change is the cavity shape. And you can see here without magnetic fields, there is no edge state. And with magnetic field, we have clearly edge state, and the isolation is almost 11 dB. So this shows for the first time that we can have topological laser using magnetic material to break the time reverse asymmetry. And it is one-way propagation, and it can have also arbitrary shape. So this work was selected as a top 10 breakthrough by Physics World in 2017. And this brings me to the conclusion of the first part of my talk, where we can show a design geometrical independent cavities. We can shrink the chip space without losing any functionalities. It is self-isolated, which means that you don't need any isolator to avoid backscattering of the light in the system. And of course, we can use it to design a very complex circuit with better functionalities. So I just want to highlight some physics that we can also use for topology that we developed 2 years ago, that in order to, like, usually generating larger topological charge of orbital angular momentum is always require a faceplate. And the resolution of the faceplate is sometimes challenging in terms of fabrication. And in addition to that, you need a laser to couple light with the faceplate to be able to generate larger topological charge. So here what we propose is to use the physics of topology, and we made something that we call topological brain, where we will alternate. We have two mirrors, trivial and non-trivial photonic crystal, again, star-shaped and L-shaped photonic crystal. And you can see here, since we designed it above the light cone, we don't need any additional component to scatter light out. And by just controlling the size of the ring, we can control the size of the number of topological charges that we can generate, as you can see here. But what is more important is you can multiplex them, which means that you can put more together and have higher topological charge because they will add to each other. This is the fabricated devices, and this is the zoom of one, and this is the experimental realization. I will not have time to go through all the detail of this work because I would like to show as a work, but just to give an overview as an application that can be done using topological laser. So this brings me to the second part of my talk, which is exceptional point sensor. So I would like to begin my talk by comparing Hermitian and non-Hermitian systems. As we know, most of the physical systems are open in nature, which means that energy can flow in and out and exchange with the environment either by radiation or absorption, which is in contrast with a closed system where energy stays conserved. And one of the fundamental differences between Hermitian and non-Hermitian systems is the fact that for Hermitian systems, the eigenmode do not decay and the corresponding eigenvalue are real. But for non-Hermitian systems, the eigenmode do decay, and consequently, the corresponding eigenvalue is in general complex. So in the last decade, we have started to bridge the physics of closed and open systems. And this underlying attention shows one of the fundamental differences between Hermitian and non-Hermitian systems, their singularities. So in Hermitian system, mode coupled to end singularities that we call dipole point, where the eigenvalue is real. But for non-Hermitian system, mode coupled to end is two types of singularities, which is dipole point, where the eigenvalue is real, but also exceptional point, where the eigenvalue is complex. So now I would like to explain what is exceptional point. It is a special property of non-Hermitian complex matrix. And when you are at exceptional point, both your eigenvalue and your eigenstate coalesce. Since it is non-Hermitian system, I would like to take a very simple case to explain how we can reach such exceptional point by considering a 2x2 non-Hermitian matrix, which you can see here on the left bottom, and use two-ring resonator to illustrate how we can reach such exceptional point. So I consider here two-ring resonator with different size. But what do we know? We know that the size of the ring will always give you the resonant frequency. We also know the distance between two ring resonator will give you the coupling coefficient. Again, since it is non-Hermitian system, we have both real part and imaginary part. So the idea here to show how we can reach the exceptional point is to look at how the real part and the imaginary part will behave as function of those two physical parameters, which is R and D. And what we will do here is to look at the real part of the eigenvalue as function of the gap D and the radius R, and look at how they behave. You can clearly see a very nice Riemann sheet here, and you can see the two modes are avoid crossing on one side, but they are crossing on the opposite side. And if you look at the imaginary part of the eigenvalue as function of those two physical parameters, you have the gap D and the radius R, and you can see the opposite is happening. The two modes are crossing on the front, but avoid crossing on the back. And if you look at very carefully this Riemann sheet, there is only a single point where both real part and imaginary part are exactly the same. This is what we call exceptional point. So exceptional point was used in different platforms, different frequency range, but very important applications such as generating single mode lasing, chirality, non-reciprocal devices, and recently also gyroscopy, which show how it can be used for something that I will come on later. Exceptional point was used in different frequency range, from acoustic to microwave, in optics using dielectric waveguide. But the questions that we ask ourselves, why we don't have exceptional point at sub-wavelength scale? But before responding to that question, I would like to respond. The first question is why we need exceptional point at sub-wavelength scale. And to respond to that, I would like to go to the next slide and come back to the two singularities that I compared at the beginning and tell you how they behave when they are subject to a perturbation. So here, I will start with dipole point, which is the eigenvalue, which is the singularities of Hermitian system. And again, a simple definition to give people like a simple definition and what is dipole point is when you have at least two modes that operate at the same resonant frequency, which is the red mode and the blue mode, but their line widths are different. This is what we call dipole point. So what happens when you perturb those modes? If I talk about perturbation, I would like to say when you change the concentration of the medium or you change the refractive index, what will happen of those two modes? So let's consider epsilon as a perturbation, again, which can be concentration change, refractive index change, what will happen? So when you have epsilon change, you will see the two modes will split, the blue mode and the red mode. But the way they will split will be always linear to the frequency shift. However, when you operate at exceptional point, again, I will give the definition of exceptional point in a very simple way, is when you have two modes that have same resonant frequency, but same loss rate, which you can see here that are exactly the same. When you perturb that mode, the two modes will split, those modes with epsilon, which can be concentration change, refractive index change, what will happen, the two modes will split. And the way they split, it is different to dipole point, because since it is two mode, you will have square root behavior, which shows that the resonance splitting is much higher than the resonance splitting when you operate at dipole point, which shows that exceptional point is more sensitive to dipole point when you use them as a sensor. To make it more general, I compare again in blue dipole point. You can see the resonance splitting of the two mode is the blue is always linear to the frequency. However, if you operate at exceptional point at second order, you have a square root behavior. And if you go to n order, you have n root behavior, which shows that if you can combine multiple mode and operate at exceptional point, higher the order, higher the sensitivities that you will have. So now I would like to go back to the question why we need exceptional point at sub-wavelength scale. What do we know? We know that plasmonic system can confine light at sub-wavelength scale. We know exceptional point can enhance the sensitivity. And the idea is here to synergistically combine those two, high efficiency, high confinement of the light and high enhancement of the exceptional point to have a new type of sensor that can detect a very low concentration. And how we implement that? In order to implement it, we hybridize two metal bars with two metal bar so we pair two metal bars here that have two modes that have opposite symmetry, which is the symmetric mode, which is associated with the electrical dipole, is that you can see here, plus, plus, minus, minus, and the antisymmetric associated with the magnetic dipole. And you can clearly see them on the right one, two modes of opposite symmetry that we have here. And what we will do here is couple those two modes to reach exceptional point. How we will do that? So let's consider the unit cell that we have here. So this two metal bar is like the two resonator as the two ring resonator that I showed before. But instead of having a ring, we have two metal bars. So we start at the beginning, two bars are perfectly aligned. So there is no offset between them. That is what we call dx is equal 0, perfectly aligned, same size. What will happen is the symmetric mode that is more radiative is in the high frequency, and the antisymmetric mode will be in the lower frequency. And the symmetric mode will have the symmetric mode are more have a repulsive character, and the antisymmetric mode attractive character. But what will happen here, because plus minus is more attractive and this is repulsive character. But when you shift to one bar respect to the others, what will happen? You can see it here in the bottom. The plus and plus will weaken, and the minus and minus will be closer, so it will be very attractive for the symmetric mode, and the opposite will happen to the antisymmetric mode. And at some point, by just controlling the offset of those two modes, you will have the symmetric mode and antisymmetric mode will get closer, and by keep changing the value of dx, at some point you will have them cross. And when we talk about exceptional point, we said we need two modes that have same resonant frequency, which means that if you make them cross, you made them at the same resonant frequency. And this is what we did here. You see the antisymmetric mode is going in the lower frequency, and the symmetric mode is going in the higher frequency. And they meet at one resonant frequency, which is around 250 terahertz. Again, we identify a first single parameters, which help us to have the resonant frequencies the same. But if you remember well, in the definition of exceptional points, they should have same resonant frequency, but same loss rate. So how to identify the second physical parameters to bring them at the same loss rate? So to do that, we consider a very simple case, which is the unit cell of one metal bar sitting on a dielectric. And we look at how the resonant frequency of this metal bar will behave as function of one physical parameters, which is py, the periodicity, which is perpendicular to the length of the bar. And you can see here, if you look at the resonant frequency is going down as function of the periodicity, and the loss rate as well is decreasing as function of the periodicity, which means that this parameter can be used because it is controlling both the real part and the imaginary part of the system. So this is what we did. So we identify those two physical parameters, dx, which is offset between two metal bars, py, which is the periodicity perpendicular to the length of the bar. And then what we did is we take the first configuration. We took two metal bars that have the same size, but it embedded in a dielectric, which is the same refractive index. But surprisingly, in this configuration, we have the resonant frequency crossing. But if we look at the loss rate, they are completely different. So we ask ourselves, we have all requirements that we need to reach exceptional point, but we cannot have it here. What happened? You can see here, the two modes that we have are two modes that are two modes with opposite symmetry, symmetric mode and antisymmetric mode. Those two modes have their loss rate so different that by just using a physical parameters, you cannot bring them together. So in order to do that, you have to change those modes to be symmetric-like and antisymmetric-like so that their loss rate are close and you can put them together. And how we will do that? By breaking the symmetry of the structure. So when we break the symmetry, we will have one bar shorter than the second one. And in this case, the symmetric mode that we have before here and antisymmetric mode will not be no longer symmetric and antisymmetric, but will be symmetric-like and antisymmetric-like, and the loss rate will be closer. So by just changing the physical parameters, you can bring them together. So what we did here is we look at how the resonant frequency behave and as function of the periodicity and the dx. And you can see here in the resonant frequency or in the real part of the eigenvalue, you have two modes of opposite symmetry, like two modes that are avoid crossing, and in the opposite side there are crossing. And in the loss rate, which is the imaginary part of the eigenvalue, you have crossing one side and avoid crossing opposite side, and there is only a single point where we can reach exceptional point. So we show for the first time that we can design a plasmonic exceptional point using an array of resonator. But again, the goal was to design exceptional point, but being able also to use such enhancement to measure or to use it as a sensor. But if you look at the configurations that we propose here, it is embedded in a dielectric, which means that the hot spot of the plasmonic, which means that the confinement light of the plasmonic metal bar cannot be in contact with any other light, because if you put a liquid here, it cannot get in because it's a closed system. So what we have to do is to be able to find a configuration that we can have exceptional point, but at the same time, we can use it for sensing. How to do that? We use this configuration. Again, you will look at the two bars, you will tell me, oh, they have the same size. We should have symmetric mode and antisymmetric mode. They physically have the same size, but optically the two bars don't have the same size. Let me explain why. The one bar is embedded in a dielectric here, which have a refractive index of 1.5. And the second bar is on air. So optically, those two bars don't have the same system. So we break the symmetry by just changing the two medium of the system and keeping the same size of the bar. In this configuration, we can functionalize the top of the bar and use any concentration that we want, and being able to use exceptional point. But to prove that this configuration works, again, we plot the eigenvalue real part as function of those two physical parameters, which is dx and py, and you can clearly see avoid crossing, and the opposite in the imaginary part of the eigenvalue. And we have only a single position where both real part and imaginary part are the same, and this is what we call exceptional point. So now we reach our goal. We have a configuration that can reach exceptional point and can be used for a sensor. So the next step is to further prove the existence of exceptional point. What we know is when you operate at exceptional point of second order, which means that you have two modes that have same resonant frequency and same loss rate, what will happen when you perturb that mode? So let's consider this. We add a cladding layer on top, which is the epsilon that I was talking about. My epsilon here is a refractive index change of a arbitrary material. What you can see, we change the refractive index from 1 to 1.2. When we operate at dipole point, again, you always have a linear behavior. When you operate at exceptional point, you can have a square root behavior. And in order to prove this is square root, you plot the log-log scale. You have a slope of 1/2 and a slope of 1, which is an additional proof that we have exceptional point, where we show it in the 2 times. We show the Riemann sheet showing both real part and imaginary part as the same. We show also that it is behaving as a square root. So now the next step after designing it is to fabricate the structure. Again, we use 3 main steps, which is e-beam lithography to define the shape of the resonator. We have metal deposition, and then we have liftoff. And we do the same process for the two layers and control the alignment very well. This is a proposed platform. As you can see here, we have 1 bar on top, 1 bar embedded in a dielectric. We use a polymer here, which is SU8, to have a very well planarized first layer. And after that, we put the second layer. And on the right top, you have the SEM image of the fabricated devices, where you can see the top bar, and you can see also the shift of the bottom bar on bottom. And in order to control geometrical parameters and the 2 physical parameters that we use, which is PY and DX, we use a dual beam, which is SEM and FIB at the same time, where we can do cross-section and image at the same time. And you can clearly see that we can control the offset between bars very, very well. We can also control the device parameters to be able to reach exceptional point. So next step is to show the first observation of exceptional point. But as we all know, mapping the whole Riemann sheet here will be very time consuming. But what do we know? We know that anytime you have exceptional point in the real part of the eigenvalue and the real and the imaginary part of the eigenvalue, you have crossing and avoid crossing on both sides. So what we will do is we will consider a periodicity, which we call Py, with 400 nanometers smaller than the periodicity where we have exceptional point. And if you look at that, you have crossing in the real part of the eigenvalue, but you have avoid crossing in the imaginary part. So if we can compare numerical simulation and experiment in this side, that will be a first result showing that we are close to the exceptional point. And this is what we did. We look at the numerical simulation here in the dashed line in comparison with the experiment. And we show crossing in the real part of the eigenvalue and avoid crossing in the imaginary part of the eigenvalue. And what is next is to do the opposite. When the periodicity is higher than the periodicity of exceptional point, you have the opposite. Avoid crossing here and crossing on this side. And you can clearly see we have a very good agreement between numerical simulation and experiment. In red here, you can see in dash is the simulation and the dot represents the experiment. And we have avoid crossing on top and crossing on bottom. And this show for the first time that we can have exceptional point at sub-wavelength scale. Again, the next step is, after proving the existence of exceptional point, is to be able to use it for sensing application. And how we will do that? We don't want to just use a sensor like refractive index change, very simple sensor. We want to sense something that are useful. So we choose to use the IgG, which is one of the most common type of antibodies that you can find in our blood circulation. And this is the flow chart how we functionalize the metal bar of the system. Again, coming back to the configuration, we have the metal bar in air so that we can fully functionalize the top of the metal bar using linker. And then this linker will capture the antibody, anti-bonding, anti-CD63, which will capture the anti-mouse IgG that will control the concentration that we will use. And then we do the measurement of our different concentrations. And you can see here, when we start at 1005 attomolar concentration, which is relatively very low, but since exceptional point, when the smaller the perturbation, better the exceptional point behave, you can see here that the dipole point is dominating the exceptional point. And by using the same sample, we functionalize with different concentration, clean and functionalize again to keep the result very consistent. We keep decreasing the concentration. You can see here, the exceptional point in red is getting close to the dipole point until at 1000 attomolar, where exceptional point become better than dipole point. And we keep decreasing the concentration. You can see that the difference exceptional point is still better than dipole point in terms of sensing. But at 50 attomolar, we see what we call linker limit. It is a very simple limit that I would like to explain, because when we start functionalizing the top of the metal bar, when we put those linker, they will all we will have a resonance shift, and the resonance shift is around 5 terahertz. So any concentration that you will add in your system that cannot bring or that cannot shift to your resonance more than 5 terahertz will be in a linker limit. Of course, that can be easily solved by considering the linker limit as a linker in your design at the beginning, so that when you add linker, you are at exceptional point and you will not have any resonance shift. In this case, we can decrease the concentration even further. But for this configuration, we consider the linker. So what happened is we consider this concentration as a perturbation. So concentration that we have here is exactly the same as a perturbation. And you can clearly see that exceptional point, since it is second order, we have square root behavior. Dipole point is linear behavior. And the log-log scale is showing you a slope of 1/2 and a slope of 1, which is, again, additional proof of the exceptional point, and showing also we can detect a concentration that is 15⁻³ nanomilligram per milliliter, which is almost 300 times better than the state of the art. So this brings me to the conclusion of the second part of my talk, where we show that we can demonstrate experimentally the observation of the plasmonic system. we can also enhance the immunodetection using plasmonic system. So I will go briefly to the last part of the talk. I would like to start with one of the most fundamental discovery of Newton, which consists of the decomposition of the white light source using prism, which is something very important for different applications, but for imaging system is a very big problem because you want to have light at the same position at the same time to focus. So how conventional optics are solving this is always by using multiple lenses that they will have different diffraction and refractive lenses to be able to solve it. But those systems are very bulky and expensive and difficult to integrate. So recently, or a few years ago, metal surface was proposed as an alternative solution to solve that. But you can see that all those proposals, the only problem they face is at that time, they can only use circularly polarized light. And they cannot have high bandwidth and high efficiency at the same time. So we ask ourselves, what can we do to solve that problem? So we said, let's review how to reach broadband achromatic metal lens first. So let's consider this system, this glass substrate. You have these green particles as the metal surface, and the focal point is here. Light is coming on the bottom, and Rx is defining the different position in the lens. If you look at the phase profile or the phase requirement at different position, by choosing the middle of the lens as a reference, what will happen is you will see that the phase requirement is always linear to the frequency, which means that this is your first requirement to have broadband. Second, the slope at different position in the lens should be different to be able to have a broad bandwidth achromatic metal lens. How to do that? In order to do it, you need to have physical parameters. You need to have degree of freedom that are independent to be able to do it. And those, to do it, we have to choose a unit cell that have many degree of freedom. And this is what we choose. And this is the unit cell that we call fishnet, and I will explain why. So how we design that, we consider 4 different unit cells. We start with this cross unit cell, and we keep decreasing the size of the width until we reach the limit. And this limit is set by the fabrication. And then we add a cylinder in the middle, and we decrease the length until we reach the final one. So those are the 4 unit cells that we use by using the degree of freedom to design our metal lens. And this is the device, the proposed platform that we will use, which looks like a fishnet. That's why we call it fishnet achromatic metal lens. And this is the fabricated devices by using 3 different main steps: E-beam, titanium dioxide deposition, since it is transparent from visible to the IR. And you can see from the middle to the edge, the different unit cells that we have. And we characterize the system. We just choose few wavelengths to show. By increasing the wavelength, you can see it is diffraction limited by comparing with the airy disk. And we show it also, it is broadband, and the focal point, which is the black dot, remains the same in the entire bandwidth. And we show here that we have very high efficiency, almost 70%. It is, the focal length remains the same in the entire bandwidth, and it is diffraction limited as well. And just to finalize, another device I would like to show by using phase change material, using a slot waveguide where we have 2 silicon blocks, and in the middle we put a vanadium dioxide. And we know vanadium dioxide, below 60-80 degrees, it behaves as a dielectric, so less loss. And after 68 degrees, it becomes as a metal. So we use that configuration to use a dual function lens and beam limiter. And you can see here 25 degrees, we focus very well. At 70 degrees, we have lens with optical power limiter. So on top is 25 degrees, on bottom is 70 degrees. All of them are diffraction limited with different power, which can be used to protect a camera. So to summarize my talk, we show a topological light sources. We can generate larger topological chart of orbital angular momentum. We show exceptional point for the first time in plasmonic system and use it for sensing and octave bandwidth achromatic metal lens. I would like to thank my group, my previous supervisor group at UCSD and UC Berkeley, and the foundation. And thank you for your attention. CSC.
Thank you very much, Professor Ndao. What an amazing, fantastic talk. And now we will shift to our next speaker. So our next speaker is going to be Professor Abraham Badu-Tawiah. Professor Badu is at Ohio State University. I just want to share the slide so I can show you. So our next speaker is Professor Abraham Badu. He is at Ohio State University, and Professor Badu is got his PhD from Purdue University, working with Graham Cook, working on mass spec, and then he went to Harvard and worked with George Whiteside, where he developed several paper-based devices. Then he joined Ohio State University and has risen through the ranks from assistant professor to associate and then to full professor. And now he's the Fox Professor of Chemistry, and also has joint appointment in internal medicine and infectious disease department. Professor Badu has been awarded so many awards. I'm not going to go through all of them. Most significant is the DOE Early Career Award. He has also been awarded the Eli Lilly Early Investigator Award, and among other awards, accolades from ACS. So without further ado, Professor Abraham, please share your slides.
Thank you very much, Martin. All right. This is my first time at iCANX, and I would say it's a great idea. Kudos to the organizers, and thank you, Martin, for inviting me. A great talk, Professor Ndao. I enjoyed your talk very much. I'm going to give you a different taste of what science can do, and this will be more of disease application. And so, from Martin's introduction talk earlier on in the program, he mentioned how to do research in Africa, you have to be really innovative because resources are limited. And some of us, so Martin and I actually did a postdoc with George Whiteside at Harvard. And so we got similar training. And I think I'm going to sort of talk about exactly what he introduced this program today. And so I'm going to focus on underserved population. And usually this group are considered less, in the race of technology. And I want to change that, okay? And so how I'm going to change it, it's not to develop any new tools, but to use my experience in chemistry to enhance existing chemical instrumentation. And so the high points of the talk, number one, is to consider the underserved group. Number two is to use a chemical approach to enhance chemical detection. And then we're going to apply it to malaria diagnosis, okay? But within the malaria, we are picking even a difficult, challenging problem, and we are focusing on asymptomatic malaria. And the people that are walking around, that it looks like they are healthy, but they're carrying the parasite around. And those are the ones that serve as a reservoir for transmitting the disease to other people. So until we are able to diagnose those people walking on the street, our chances of eliminating malaria from the continent of Africa becomes really challenging. And this project actually started in 2019. My collaborator, Kingsley Badu, which is not related to me, but we are working together. My student, Aisha Sith, has worked with me for almost 5 years now, and I'm the PI for the project. My collaborator works in Ghana, Kwame Nkrumah University of Science and Technology. Okay, so my background, as Martin mentioned, is in mass spectrometry. And so that is what I want to use in this area of asymptomatic malaria diagnosis. But I'm applying it to the underserved group. And there are several groups within the underserved population. Ethnic minorities could be one, young adults. Today, cancer is affecting young adults. And we need to find a way to actually diagnose them. Elderly people, they have their own issues that we have to reach them where they are. Babies, for several reasons, it's extremely challenging to work with babies, mainly because you cannot take a lot of biofluid from them. So how do you work with a drop of blood from a baby? Very challenging. And now in developing countries, because of limited resources, it's very challenging to do high quality research. And so in this talk, though, I'm going to focus only on developing countries, although the technology that you hear today could be applied to many other underserved groups. And again, these groups are usually ignored or they are considered last, in the technology race. And I want to kind of break this trend. And so in considering malaria, we are making progress. The number of deaths is decreasing gradually, but the incident, is increasing. So there's still a lot of people that are infected with this disease. If you go back to 2016, this trend was very different. In fact, in 2016, we thought that certain countries could reach elimination by 2020. So in fact, WHO established what they call the E2020, where they identified about 21 countries that they thought could reach elimination. Well, 2020 came, and only two of these countries had reached elimination. What happened? Well, we really didn't have the tools to diagnose the people at a low level of the parasite to be able to tell who is getting the parasite, who is not getting the parasite. By the time we realized, the whole trend has gone up again. And so now they've reversed the trend, the program to 2030, and they're inviting people to come in with a more sensitive tools to help with diagnosis and surveillance, for the program. And so that's why I think that a sensitive tool for asymptomatic malaria is necessary, for the elimination of the disease. Okay, so why did they fail? Currently, at WHO, or the program that I work in is operating based on WHO's assured program, which is defined here. Assured, meaning that affordable, sensitive, specific, user-friendly, rapid, equipment-free, and deliverable. Yeah, so they say that if you are working in the developing countries, because typically these countries are poor, this is the criteria you have to follow to develop the technology. Well, if you strictly follow this criteria, the best you can do is to work on RDT, to take a plastic, put the antibody on, put the blood on it, and then the blood will work through, and you capture certain antigen, and the color will change, and you read with your eyes, because they don't want you to use any equipment. You read the result with your eyes, and the best you can do is only when the disease is really, in a high point. If it's asymptomatic, when the parasite density is low, you're not going to be able to see any changes. That is a reason why the current technology is failing in helping in the effort to eliminate the disease. And as a chemist, or as someone who was trained in analytical chemistry, I take an issue with that, to not be able to use equipment. Yeah, Africa is poor. It's resource limited, but to limit an equipment to not be used, I think misses the mark, because the tool that we come up with is actually not effective. In fact, in my opinion, in my humble opinion, I would say that this assured program is operating in this quadrant, where they want us to develop a low-cost method, and the result is that we get low value. The tool doesn't really work well. I think we all agree that if you want high value, it usually comes with high cost. And so what we are doing at Ohio State is to reverse this trend. Yeah, we agree with WHO, we want low cost. So we are trying to get low cost technology. But how do we keep this low cost technology to get high value? That's a question nobody is asking, and that's what we need in Africa. It's not just to remove equipment completely, but we want the equipment to be able to give us the results we need at a reasonable cost. And that is a challenge that must be addressed before we can eliminate any disease, from the continent of Africa. And so we've been working on this for a while now. And so how do I do this sustainably? Okay, I grew up in Africa, and I know that resources are limited. Yeah, but how do I get high value out of sort of low cost methods? And how do I do it sustainably so that people can afford it? Again, for even the challenging cases of asymptomatic malaria. And so I'm going to use a portable instrument, not as expensive as the traditional equipment. It's affordable. Plus, if I get one of these instruments and I put it at the center, many people can benefit from this one equipment. In fact, I can actually estimate millions of people could benefit from this one equipment. Therefore, the cost per test could actually be considered very low if you consider one instrument being used by millions of people. And so the way you do it is you go to the villages and you collect samples and you bring them to the center and you analyze it. Since our focus is asymptomatic malaria, there is no urgency to diagnose and give results immediately. These are people that are already walking around as if they are healthy. And so we have time to analyze results and communicate the results back to them and advise them to seek medical attention, if need be. And this one could also be used in a large-scale screening process, so we can now get effective data. And so to do this sustainably, millions of people will share one equipment, but also to actually make it more appropriate, we integrate many things into the device. I will show you on the next slide. It has to be inexpensive. Okay, so we are using paper substrate to do this, to collect the samples from different locations and bringing it to the center. And then the sample that is collected onto the paper itself is stored in the same paper and at room temperature. One of the challenges in Africa is, of course, is power. And storing samples at cold temperatures is challenging, even in the US. And so if I can enable the samples collected to be stored at room temperature, I eliminate significant part of the problem. And then once I'm ready to analyze, I analyze also from the same paper using a portable mass spectrometer, a portable instrument that is affordable and could be used anywhere. And so by integrating all these three parts, we are able to get high value out of low cost material, even like paper and others. And so, the question that comes up quickly is that most disease biomarkers, the antigen themselves, are usually proteins. Okay, they are proteins. And portable instruments actually have low mass range. Okay, which means that typically you cannot use a portable instrument to analyze proteins. Okay, to analyze the protein themselves, you really have to use a high resolution, large, expensive mass spectrometer, which I agree is not available in the resource limited settings like Africa. And so the question is, how do I use a portable instrument to analyze large proteins? And the solution is to use a cleavable ionic probes. So here's where the chemical approach comes in. And so it seems like almost impossible unless you think deeply about the problem. Yeah, so we're going to use antibodies just like everybody else uses. Even the RGT is also using antibodies. And the antibody captures the antigen here. And then we bring a second antibody, which is conjugated to the ionic probe. Okay, and that also binds to the protein. And now we have a sandwich amino acid with the ion bound to it. But this ion is cleavable. Okay, and here is a structure for the ion. The ion that we really want to detect is this part here. And it's linked to a conjugate unit with isothiocyanate group on there, which allows us to bind the whole ion onto the antibody. Okay, and so we use this antibody here for amino acid. And once the amino acid is done, we change the pH to cleave this ester bond. And so once this bond is cleaved, it releases the ion that we want, a small ion. That mass of this small ion is reasonable to be detected by the portable instrument. Therefore, instead of using a large expensive mass spectrometer to analyze a big protein, which is not likely in Africa, we detect a small ion, which is possible on a portable instrument. And so this problem now is solved. And as you can imagine, we can put several ions onto this antibody. So every single antibody that binds can come in with several ions. So the sensitivity also goes up. And here's the interesting part. Since we synthesized this ion in the lab, we made it up. So the mass is known. Okay, and so we already know what signal we are looking for. And we can change the N also to change the mass as well. And so when we are looking at the results, it's just yes and no, because we already set the mass and the instrument is telling us, okay, this signal is there or it's not there. And so the interpretation of the results is not that difficult anymore. Anybody, nurses, doctors in their rooms could actually look at the results and say, yeah, this is positive and that's negative. And then they can use the abundance of this ion to also quantify how much of the protein is there. And so again, the protein themselves will be difficult to be analyzed on a portable instrument. We are using a cleavable ionic probe that we can cleave, and the mass is set to be small to be comparable to a portable instrument to be analyzed. And so this is what we are doing. And so there's more important aspect of the technology in that traditionally, okay, in the traditional RGT method, they usually use an enzyme to change the color so that the result is visible or not visible to your eyes. And that enzyme is typically not very stable at room temperature. It degrades very quickly. But in our case, we are using a probe. It's an ionic probe. It's stable at room temperature, stable at high humidity, stable at all different conditions. That means that we can do the analysis on demand. Okay, the process can be interrupted and then stored and restored anytime you want. Okay, so I can go to Africa and take results and take samples in the villages, and bring that sample to US and analyze, and no problem will happen. I will get the same results as if I analyze the results in Africa. Or I can go to villages, remote villages, in the country, collect the samples, bring the samples to a central location and analyze in days later. And I'll get same results as if I analyze in the same day when I collect the samples. That gives us a lot of opportunity for few health professionals to analyze thousands of patients without having been limited by time issues. So our method, in fact, is time insensitive. You get the same results regardless of when you analyze the data, which gives us opportunities to do many things with this. And just to emphasize, to say that this stability is actually the crucial part of our work, because in analytical chemistry, traditionally, even if you do this in the US or anywhere where you have resources, the error in your measurement is actually 60% of it is coming from the stability of your sample. If your sample is not stable, you're most likely going to get errors. In fact, this happened to us. So I told you that this project started in 2019 before COVID. And so we're supposed to go to Africa and get data, and go to Ghana and collect samples. We couldn't go because of COVID. So we told our collaborator to collect samples from Ghana and ship them, liquid samples, ship them to us, in the US for us to test the devices here at Ohio State. And guess what? 3 times they ship the liquid samples on ice. By the time it gets to the US, all the samples are destroyed. They all lies up. We change the vendor, the shipping company, the same thing happens. Until we paid almost $5,000 to actually to get extra ice and to safeguard the samples. Even when that came, we got only 6 good samples, to analyze. All of them not good. In fact, this paper here, you can read it for yourself. It was one of the difficult papers I could write, because in the paper we said we collected 200, samples, and yet result we are showing only 6 of them. And reviewers don't understand why you collect 200 and you are showing only 6. Well, it was the 6 were the good ones. The rest are not good. And so if we can keep the sample stable at room temperature and analyze anytime we want, that solves a significant problem in analytical chemistry, which is what we want to do also. And so here is the device. It's a paper fluid device that we are using to collect the samples from remote areas. The immunoassay itself is automated, so the device can split the sample, in this case, into 4 zones. It can store the reagents, all the reagents we need within the device itself, and we don't need any external pumping. The capillary action in the paper just passively pump the fluid from the top all the way to the bottom, and the assay is happening, and we can do multiplexing. And the detection is also coming from the chip itself. So let me explain a little bit more what this device is doing. So the top layer, this one you see here, is sort of a ruler. There are 2 flows. When you put the blood on top, some will wick laterally and some will wick vertically. And so we can tell through the lateral flow, if it gets here, we've calibrated that, okay, 20 microliters of blood has gone down, okay, and then we stop it. And then we use the 20 microliters for the assay. Okay, on top of this paper here is a plasma separating membrane that try to remove the red blood cells and allow the plasma to get to this point. Once the plasma gets there, it gets split into 4. So it goes here and there and there, and the black areas are all hydrophobic, so the plasma doesn't wick in the air. The white areas are hydrophilic, so the plasma just wicks there. Now, once it gets to this point, this is aligned to this. This is aligned to that point also there. Excuse me, I lose my computer is frozen. Oh no.
No, we're good. Keep going.
Yeah, but it's not going to the next slide. Yeah. Anyway, let me keep going and then see what I can do. So yeah, it's not going to the next slide. Anyways, once we get to the reagent layer, we have stored all the reagents on this. Yeah, my pen is not writing either.
Can you try to light click it and get away from the pen?
Let me see. One moment, please. I don't know what happened right now. Okay, I've stopped sharing. Let me try and share again. Okay, can you see it?
Yep. Go ahead, Abraham.
Yeah, sorry. It looks like there's something. Let me close. Oh. Okay. We should be good now. Okay. I apologize. Okay. So I apologize. I have no idea what happened. Okay. So it gets split. It comes down to this area where we've stored every reagent we want, and then it redissolves this reagent and it carries it along. And we have a dwell layer here to allow the reaction to keep going. And when you get to the capture layer, that's where we have the capture antibody immobilized, and everything that is coming will be captured there, including the ion. And so all the layers are bound by a double-sided adhesive tape. So this is very easy to separate the individual components and analyze them. And so we detect on this last layer, which is the detection layer, which is through a paper electron spray process. The sample will come down to the center, and then we apply a high voltage, and then we release the cleaved ions, and then we detect. Okay, so you can see that from this single paper device, we can diagnose different diseases depending on the antibody that we put onto the paper. But for this case, okay, for this presentation though, it's only for malaria. So we use 2 of the spots for positive samples, 1 for negative control, and another one for positive control, for calibration purposes. So let me show you the results then. And so here is a results from the portable instrument compared to a benchtop real instrument. Okay, and the sensitivity when you analyze directly from the paper, comparing to picking the solution up and analyzing through sort of commercial way. So the portable instrument is about 10 times less sensitive than the commercial instrument, but that's okay. Okay, so 10 times less sensitive, but that is enough to diagnose asymptomatic malaria. Okay, that's about 200 parasite per microliter of blood. But our goal, it's not really to diagnose symptomatic. We care about asymptomatic, where the sensitivity is actually very low, 200 picomolar. And so this is not enough. Let me show you how we analyze from the paper. Looks like it wouldn't play, so let me go forward then. So in this case, we're limited in sensitivity, but we have to improve it by doing a signal amplification. And so, in the previous work, the ion was attached directly to the antibody, and that kind of limits the number of ions you can detect. But now we can do simple chemistry by using a dendrimer. A dendrimer had about 64 amines on the surface, and each of them can be used to bind to the ion. And so we use this chemistry to get us there. And then in the end, this reporter antibody with the dendrimer attached has at least 60 or 50 probes. So each one antibody that binds gives us a minimum of 50 probes. And when we use this antibody for reactions, now our sensitivity is within what WHO actually wants. It's less than that. It's actually comparable to what PCR will use. The difference is that PCR will amplify the analyte and requires kind of excessive temperature control, reagents, all of this. We analyze the signal. We amplify the signal, which is easier to achieve anywhere you are. And so now we are good. And so we took this device and we went to Africa to test this device. My time is almost up, but let me finish with this, Martin. And so since 2019, this project has been ongoing. My collaborator has been going to the villages, kind of preparing them that we are coming there to do the project. We've talked to the chiefs and the people, so they know that we are coming. When I arrived, I was really impressed. I went to Ghana. When we're trying to get funding for this project, people thought that you couldn't possibly use a portable instrument in Africa because there's no power. But that's actually not true. It depends on where you are. And even this is a remote area. There's power supply everywhere. I could easily set a mass spec in this, and get results. I was very happy to see this improvement, and people showed up. People were interested, because when I was going, I was worried that, okay, I'm looking for asymptomatic people. They are not sick yet, so why should they come and do the test? But they actually wanted to know their status. Perhaps they saw someone, a diaspora, somebody who looked like them, come back from similar village to show them a technology. Everybody was interested. I mean, children were interested in even doing this. People showed up so much that sometimes we have to stay night to actually complete the test. I went alone, that was a mistake, but actually the students in this university were capable. So I went alone, but I trained them there and were able to do everything that we're supposed to do. And all of them are now, actually 2 of them are doing PhD now. Amazing results. It was a great experience for me. It was humid, it was hot, but there was no problem. The paper devices worked well. I recruited this student also to help me in the device. You can see me sweating profusely, but it was worth it because we've gone back. In 5 weeks, we were able to sample 500 people. Turnaround, as you saw, was great. They trusted us. They saw someone that looked like them come back. There was no one iota of doubt that I was coming to do what I told them I was coming to do. Everybody was happy. They were genuinely interested in their status. We asked them, they usually wanted to know whether they were sick or not sick. Sometimes we're too busy to tell them, but they will come back over and over and over again to get their results. They just wanted to know. It was amazing. Well, we give them some milk and some soap, so maybe that was also part of it. But the diaspora thing was amazing. That somebody have come back from the diaspora to test these results. We set up table that went all the way to this room. And when they come, we have to identify them, the house they're coming from. That was a difficult part. And then measure their temperature, their blood pressure to make sure that they are okay. And then we go through the sample collection. We did several different tests. So WHO wants us to do the RGT. So we did the RGT. We also did PCR. We did microscopy. And then we also did the paper test. It was a lot of work. But Martin, if you allow me, let me finish with some results from the field studies. And so we tested 3 different RDTs. The BioLine is a conventional RDT that people are using for such tests. And there are 2 new ones that are developing. We bought those as well. This is supposed to be sensitive RDT, and this is for sort of a 2-line, sort of multiplexing RDT. And we're going to compare with PCR. And here's the results. Let me just focus only on a conventional. So a PCR says that there are about 79 of the people were positive, while about 110 were negative for this community alone. But the RDT, look, there's a lot of false negatives. Why? Because the test is not sensitive. People have the parasite, the device is telling them that they don't have the parasite. This is the problem. And the disease keeps on recurring over and over and over and over again. And so our goal is to reduce these false negatives, to develop a sensitive tool that can actually maybe be comparable to PCR. And we are working on it. Let me skip this to say that we've done a statistical test to show that the agreement between these two are just modest. If it's good, then it has to be about 1, but the numbers are very low. We are still analyzing our results, trying to figure out how we should actually come up with that data. I told you there's negative control, there's a positive control, and then there are 2 tests. Okay, and so we divide this positive control by this, we get a noise, we multiply by 3, and then we compare this 3n with our test results, the average of the 2 results. So for example, the 2 test results, here's a test result, here's a positive control. Okay, we should see these 2 peaks. That should tell you that that's a good device. And for the negative control, you shouldn't see those peaks. There should be nothing there. And then for the test itself, we see the same signal compared to the positive control. That means this is a positive test. If you go to negative test, well, yeah, there's something there which is comparable to this, but the signal level is very low compared to the negative control. So if you find a ratio between these 2, it's very comparable to the ratio between these 2. So we assign this as negative. And then when you compare, so just a rough comparison, when you compare our method to the conventional RDT, we get positive about only 23. We are getting 43 positives from our method. It's not 100% compared to PCR, and we are still working on this. At least it's an improvement in reducing the negative, the false negative that we are getting. So in conclusion, I would say that we've developed an affordable device that potentially can give us excellent results, with relatively inexpensive materials. As of today, we can do symptomatic malaria, no problem. We are hoping to really do asymptomatic. That's the goal. And then hopefully the next program is to apply it, in screening even larger people, in the hope to kind of eliminate this disease. And so in the end, I have a lot of students doing this funding and have supported me through this. And I will end here and I will take questions as the time comes. Thank you so much for your time. Okay, Martin.
Thank you very much, Abraham. It's always fascinating to see this amazing work. And so I will invite our panel to join us, and we can continue with the question part of this. So I would like to invite, let me share the slides so I can introduce them. First, I'd like to invite Professor Edwin Fortang. Edwin is an associate professor in LPI. He studied his scientific career in Russia, obtaining BS and MS degree in applied physics, and then moved a little bit east to Germany, where he got his PhD and then moved really, really, actually west, not east. He moved really, really west to all the way to Los Alamos, where he later on was jointly appointed at Los Alamos Labs and the University of New Mexico State University, where he was an associate professor before moving to RPI, where he has continued his work. Our next panelist is Professor Femi. Femi is a tenure-track professor at the University of Twente. Femi has trained at University of Cambridge, the Cavendish Labs, and he is an expert in optics and nanophotonics. So, and he's originally from Nigeria. Edwin is originally from Cameroon, but now here in the US. Our next panelist is somebody who is dear to me. Is my former professor. So Abraham, if I have anything messed up in my mass spec, here is the person to blame. Professor Ruth Wanjao got her PhD from Wuhan University in China, and then moved back to Kenyatta University, where she is now associate professor in the Department of Chemistry. She has a huge passion in mentoring young scientists and young women. She's very active in peer counseling, has raised a few grants, and has been PI of some major projects, and is very, very involved in analysis of foods and essential elements and like vitamins, and also environmental analysis in Kenya. Welcome, Professor Wanjao. And our next panelist is a professor in architecture from Jomo Kenyatta University. Dr. Karanja is in landscape architecture and design, and as is the theme today, beyond being very well trained in Finland and New Zealand, he's back in Kenya where he's leading some effort in bringing smart structures, especially to the less vulnerable in the community. And Professor Karanja is going to be joining us to discuss about interdisciplinary science beyond the traditional boundaries of science and technology. So welcome, everybody. The last panelist just stepped aside for a minute, but she will be joining later to talk about the role of government in African science. So welcome, everybody.
Thank you, Martin.
Yep. So the floor is open for questions. Anybody has any questions or comment on the talks for our speakers?
Okay, thank you, Martin, for that, and Professor and my former student. And I want to really thank Professor Ndao and Abraham for that, those very wonderful and very thought-provoking presentations. I have a question for Professor Abraham, and it's just a question of the instrument that the portable MS. And I was wondering about the electricity issue of it. And I was wondering, is it possible for them to come up or to get some batteries so that they can, even if they go to the remotest part of their country, they can still go ahead with the analysis or the good work? Thank you.
Yes, thank you, Ruth. Professor Wanke. Yes, that's a great question. And yes, the device that we have actually could be operated on a battery. It's easy to actually charge sort of a UPS system, and take with you over there and plug it in. Within few hours, you could be able to kind of analyze all the results. Now, the most interesting part of the portable instrument is that for the commercial large instruments, they always have to be running. Okay, if you turn them off, their performance is not good, and that is actually part of the cost. They have to be running constantly. That is not the same for the portable instrument. For the portable instrument, you turn it off when you don't need it. You turn it on when you need it. And when you turn it on, within 15 minutes, it's ready to be used. And when you don't need it, you turn it off, you put it on the shelf. And so it really saves energy. That's why it's actually feasible to use battery, in the field and turn it on when you need it, analyze when it's necessary, and turn it back off. And so yes, it's very possible.
Very good. Maybe I can jump on that question, because we all rose from the continent. We all rose from Africa, and what's interesting between the two fields, and the reason why we are very excited for you, Abraham, and Abdoulaye to be here, is you're working on very different fields. Abdoulaye is in high-level optics, lasing, and really advanced, what would look very heavy physics. You take a very chemistry approach to do your work. And what is very clear from both of you, you're fighting one question: sensitivity. How can we get better signals? How can we get to detect something that is so dilute? And what is fascinating with both of you, I see both of you are working with IgGs, antibodies. So it's very clear, disease burden is very clear in your mind. Maybe I pose this question to both of you. How does coming from Africa affect how you think about science? Do you see something that you somehow gained by being there that is influencing the way you think about solving problems? Both of you can jump in.
That's a great question. Abdoulaye, you want to go first?
Up to you. I can go. You can start if you want.
Okay. Let me take a stab at it. So that's a very good question. And actually, I would say that my research is governed solely by how I grew up in Africa. In fact, I have a program, as you saw, that I have several different underserved groups, elderly people, young adult, babies, all of that categorized as underserved, including the developing country, which we had today. And among all of them, what is governing how I design my experiments is I say I'm developing a science in reverse. So a science in reverse, what I mean is typically when people do science, for example, in my case, I was trained as a mass spec person. Mass spec, actually, I didn't have any experience with applications, very purely fundamental mass spec. And that's what typical scientists will do. We will go forward with what we know, and then we just do whatever is possible. But what I'm doing with the science in reverse is to look at who can benefit from my work, and then develop methods that can suit their needs specifically. So I'm not just doing this and that and that. I'm looking from babies, and I'm asking, okay, what do babies need? And how can I design experiments to benefit them? I'm looking at developing countries, and I say, okay, how can I develop experiments to benefit them? And of course, I got this idea because I grew up in Africa, and I intentionally want my experiment to actually benefit them. And so this science in reverse actually works. It works in so many different areas. It works in even training students. The way that you train students, if you could look at a student and work with them from their perspective, it works really well. It works in writing grants. If I can think about a reviewer perspective and write from their perspective, that also works. And so, yeah, it's really governed my research, science in reverse, because of the experience I had in Africa and the intention to make a difference there, which is now being applied in so many different ways.
Right. Thank you very much. Abdoulaye?
Yeah, if I have to add something, I think being like coming from Africa will teach you how to do things without money. We learn from when we are very young to be very creative in different ways. Even the toys that we use to play is something that is not something you can buy somewhere. You have to fabricate yourself. So you start learning, having some skills without even knowing what to do. And when you get to the school, what you learn is, since you don't have the possibility to do great experiment and stuff like that, what you will learn, you will have a very good foundation in math and in physics. So your theory background, your math background will be so solid that anywhere you can go, it will be for you very easy to understand things. And that can help train like very well any students that come from Africa and go to other countries, because the foundation is very, very strong. And like that is something that I think is in either way we should find a best way to use it, as having those young kids that have a lot of talent but don't have chance to explore those big labs that we are now, that using new, like again, most of them never see a laser that is working or fiber optics that is working, but they understand all physics and theory behind that. So giving them the chance to be able to travel to see those and explore different way of doing science will help a lot. And again, that gives me the foundation of my background that helped me to do a lot of things that I'm doing now.
Thank you very much. And actually, on the same thread, if I can bring Dr. Karanja, Dennis into the panel, it's something that is the idea that you're very broadly trained to solve a problem. You become almost discipline agnostic, and you find yourself, Abraham, it's very nice to see you solving epidemiology problem from chemistry. Yet I don't expect that during your training you attended epidemiology classes, or you ended up doing medicine, right? Looking at the papers that Abdoulaye is putting out on mental lenses and lensing, I don't see that as something that a medical student would do. But then I look at his papers, I see stuff about IgG and antibodies and sensor development. And so coming to Dennis, we see that as African scientists, we become discipline agnostics. We work across all disciplines. And I wanted to ask you, as somebody who is more into the tech, into the civil structure, civil engineering, how do you see the interdisciplinary sciences coming into play in fields that are so far removed from each other? And how can we as African scientists participate across different disciplines to break those barriers so that we can solve problems irrespective of the definitions that we get from our training and the Western way of thinking? How do you see that coming into play?
Thanks, Martin. I'm looking at a resource to what Professor Badu mentioned in terms of trying to build value from very low costs, and also working with accessible resources, but building value from that. The other thing I'll think about is affordability. We should be thinking about affordable science, and not just affordable science, but transformative science. And that is science that's accessible to the majority, which is relevant to the poor populations. And also, when you start thinking about access, you're thinking about a tool that is valuable and is accessible for perhaps diagnosing very many diseases. And that's more or less my research to Professor Badu. But coming to thinking about interdisciplinarity, one, I'd say that there's one area we are linking chemistry and material science, and I'll come back to that, trying to link chemistry to architecture. But on a general note, no one will rescue Africa. So we have to make do with the human resources that we have. We have to make use of the technologies that we have. And we have to start thinking across variants. Like, if I have to think like an architect in terms of design, I have to rope in other people who are like-minded. They might not be designers, but there could be solving problems that are associated with architecture. Let's say housing, for instance. So you have to collaborate for you to be able to do that. And you cannot collaborate only with those people you share the same kind of training. That will not help. The other thing is we cannot reinvent the wheel. I'm looking at what the presenters are working through, and I'm seeing they are not trying to build a mass spectroscopy machine from the scratch. They are taking it to the next level. What kind of additives can I use to get a similar kind of results with very low resources? So we cannot reinvent the wheel in that sense. So we basically have to collaborate with those who have the knowledge. And these could be way out of our disciplines. And I'd say in our context, what you're doing is we at the Center for Integrated Prototyping and Innovation at my university, we look at rapid prototyping as one of those areas that you could collaborate in, test ideas, make them tangible and accessible. So, Martin, I think I'll leave it at that for the time being.
Thank you very much. And I think that idea of disciplinarity and getting out of our comfort zone is something that we have a mandate to push. And so on that note, we also have a lot of young talent, younger than us. And I look at somebody like Femi, who is also in the optics world, and I wonder, how do we mentor the young talent, and how is that young talent going to engage with the continent in a way that goes beyond the traditional barrier? So maybe, Femi, I can show this to you, and maybe you can comment about how you see the role of the young scientists, both at home and abroad, in shaping the narrative about African science, and what we can do about it as a team.
Right. Thank you, Martin. Yes, I will be really glad to talk about this, but I have actually several questions for the speakers. I really enjoyed the talks a lot. But one question I would just throw out is there a possibility to combine your two methods? So Abdoulaye is working on these photonic structures that is quite sensitive at the singularity point. And then would that be possible to combine it with the Abrams method and maybe then use some other spectroscopic techniques together with mass spec, for example, surface enhanced Raman scattering, and maybe that will enhance the sensitivity of the method. But it's something to think about and to discuss about later. So about the talents that abounds in African countries. Yes, indeed, we know that. Yes, there are a lot of young talents there, and they are being actually exposed to what is going on outside now much more than before. The internet connects everyone. They can get a lot of information. They even when I was a bachelor student in Nigeria, I was already looking for lecture notes from other universities abroad. So that was 15 years ago, something like that. So right now, I can imagine that there are even a lot more resources for them. So like Abdoulaye said, maybe they might not be able to conduct really great experiments in the lab. They might not be able to operate the most high-tech equipment. But there are some really very important traits or characteristics that growing up in Africa just gives you. If you are the type of person that is curious and wants to know a lot, then there are a lot of information now for the young people to know. So they are already very well informed. They know about how basic principles of some of the equipment that we have abroad that they don't have access to. They know how they work, and just giving them the opportunity and the exposure to work in this advanced research environment would be really very useful for them. And also the fact that someone have not operated a high-tech instrument before does not mean that they cannot learn it quickly. So there are transferable skills, right? So maybe during their bachelor project or during their education, they did some work. Maybe they developed a very crude crude method using the little resources they have. That's what you need to see that, okay, this guy have done something really cool, even with the little resources, with the little available materials, this person that is so determined and is so driven, then give them a lot of resources, then they will do a lot. So that I think is the message that the outside world should know. There is a lot of talent out there in the African continent, and just being able to give some of them the opportunities will make a lot of difference. I think all the speakers today, at some point, they lived in Africa, and they were also looking for opportunities. Somehow they got opportunities. I don't know their stories. In my case, I got a scholarship to study in Germany, and that was the opportunity that exposed me. And many people are there, and maybe the next person that will solve, that will find the cure for cancer is also just looking for opportunities at this moment, saying, when would I be able to get to see all this equipment that I've been reading about, all these places that I've been researching about. And this then goes to professors. Maybe you have an opportunity and you get some email from someone from Mali or from some African countries. You might want to think a little bit, okay, maybe this person hasn't done the kind of experiments that we're doing, but yeah, they've done something with the limited resources. They might also be able to cope in this situation. So in the past 5 years, at least for Nigeria, there is this thing called YAPA. So it's really Nigeria is just moving outside of the country to look for opportunities abroad. So I think we will see a lot of Africans in conferences and doing really great research in the coming years. So that's very promising. I would like more to see, for example, when the two speakers were talking, I was like, this is really cool, especially Abdoulaye, because our fields are quite close. And to see a fellow African doing all these interesting works, I was like, this is really, really amazing. So I think there are there can be more Abdoulayes in the future. There will be more people like this that we will be seen at conferences, and that will be doing great works. Also, like Abraham, also not just forgetting home, but also giving back home, solving problems at home, like Abraham is doing, which is also really nice. But there is the place of mentoring, because when people go abroad, then it can be really very lonely. And trying to find each other and helping each other wherever we are. So that's how I got Martin. How I got to know Martin. I think that can be very helpful, being supportive. I think people from other countries often do that. People from India, from China, they often form a team together, helping each other. I think if Africans also do this, it would be really very helpful for us.
Very, very good. And I know we have a lot of technical questions and comments. So if you have any question to our speakers, please take it up. And Edwin, maybe I can ask you to comment about how we rise from the continent and do very advanced sciences, but be able to engage with the continent through different forums. Like, how do you connect back? We left. Some of us left in our countries when we were very young. We went abroad. Others have come back, like Professor Ndao and Professor Karanja. They moved back to the continent. Others are still in the diaspora. Yeah. But as you stay away for so long, you lose contact, right? Some of the professors you knew, some of the people you knew in the field have moved away. And the other thing is, you're also not informed about what is happening because the disciplines shift so much. You look at how you left Africa. You were in one area of interest. You move so far away, and maybe you don't even know people in that field. So how do you connect? How do you bridge the gap from the diaspora to the African scientists? And on this forum, on iCANX, we've hosted quite a number of Africans, all the way from Terry Chibare, who is a medicinal chemist, to bring in Bara from Senegal, who is a nano material scientist, to somebody like David Dodo from Ghana, and somebody who's now in energy, nanomaterials, Dixon Andara from Kenya. We've had a very talented a woman from Mauritius, Luxman Bo, and these people do exist in the continent. Mm-hmm. But those of us in the diaspora who have access to very high-tech resources, we sometimes don't even know. Mm. And for those who are of non-African origin and they want to connect with the continent, what are the forums they can use to connect with African scientists? There's a scientist in China, there's a scientist in Germany, somebody in the US who wants to connect to an African scientist. How do they do it?
Yeah.
Yeah.
Yeah. So thanks a lot, Martin. It's a very good question. So it's a little bit hard to put it in one box to explain it. So first of all, let's talk about the challenges that we face as faculties and scientists, in Europe and in the US, in the Western world in general. So for most of us, I think Abdoulaye and I, we do a lot of work together. We've overlapped recently. So our ascent to wherever we are right now, to tenure track or to industry, it's not very, very easy, as you can attest. There's always that battle that you're facing to prove to your colleagues, to prove to the rest of the world that you belong, that it wasn't handed to you. So one thing that happens to most of us is that during this process of fighting to become tenure, of fighting for publications, of fighting for grants, we become transformed by the system. So there's just it puts you in that small box of your own, that box of just connecting with the experts and the folks who actually would get to review your papers, review your science. So it isolates you. That's the first thing. Because there's a good and bad side to that. So the good side to that is that for you to be able to reach back and help back at home, you need to be in a position of power. You need to be established. So if you are an early career from Africa, you're still rising. It's really, really hard as a postdoc, as a grad student, as an early assistant professor to be able to help and build your research. You can do both, because to build your research group, you need to hire students and postdocs who are trained, who are experts in the field. So there's one of the issues that most of our folks back home, like Abdoulaye mentioned, they're very, very smart in theory, but they need a little bit of time to get up to speed, to run the lab for you to get to that position. So there is a little bit of that uncertainty that you have to try to balance for you to advance. So one thing that could help that I've noticed is that if you are involved in a community like what we have right now, where you have access to some senior faculties like us and junior faculties, then there's a little bit of that bridge where you could reach out and say, hey, I am looking for such and such a student, such and such a postdoc. Can you recommend someone from Africa who is skilled, not somebody who has to learn? At least that's a good way to start. I did that with Abdoulaye and Musa, and I have a postdoc coming from Senegal. But you can only do that when you're comfortable, when you're able to. So that's some of the challenge that we face being out here that gets us disconnected in the process of trying to become tenure, trying to build your research. You isolate yourself. So it's almost inevitable, but I hope we can learn from that. So that's the first thing. Then for the students who would like to reach out, so personally, I think Abdoulaye has similar things. Musa, we get a lot of emails from folks from Africa, from Mali, from Nigeria, from Cameroon, and from all over the continent. You see most of those students, their desire to do science and their will to succeed is much more stronger than their preparedness, how prepared they are in terms of how ready are they to face the system. And this is usually due to the fact that we haven't informed them about what it takes to compete out here. For example, there are some basic rule of thumbs, like you can apply to some state universities, some universities where you have a better chance of succeeding, and then you can jump ships and move to Ivy League and top schools. But you have most of our folks who are really, really good. They're just not informed. They'll apply to the MITs, the Rensselaers, the Boston universities, and they wouldn't go through, and then it would discourage them. or they would send an email to a faculty who is in those universities and he wouldn't respond, and they would be discouraged, saying that those guys don't care about us. So it's just a level of difficulty that has to do with the fact that we are here fighting with a system, and by the time we get to change the system, we're already so isolated that we don't know how to reach out. We're just comfortable in our own spot, and then they are also trying to fight a system to get in. So it has to do with information and communication. So like I left after high school a while ago, and I have been disconnected. Really, I just started getting connected back to the continent after I met with Abdoulaye and with Musa. Musa and I happened to be faculties in the same university. So the past 2 or 3 years, I started reaching out. So the best I could do personally was to hire a couple of students from Cameroon and mostly from the Soviet Union and from Germany. But just getting connected to, meeting you last year and meeting the rest of the folks, it becomes sort of easier right now to understand what's happening back at the continent, how I can reach out, and how I could actually help build my own research. So it's not an easy problem to solve, but it is solvable. That's what I could say. But the major issue, hindrance in the path would be politics. So, for example, I don't know how it is in most of the other African countries. In Cameroon, for example, if I make an attempt to reach out in universities or companies to get students, there's always that political barrier that you have to overcome, meaning that you need to have someone out there that you trust, that is able to select the folks that you like, or just transfer the information as undiluted as it is. And it's not so easy. So then at some point you just give up. I've had more success in dealing with Senegal, for example, than dealing with Cameroon, which is my home country. Just because I have Musa and Abdoulaye and a couple of guys who understand the system, and they get me connected to the faculties themselves. So if we can get beyond the politics, then maybe we can do something for the continent. And I think so. That's sort of where I see it personally. But yeah, there are opportunities, and I hope we can reach out to most of the folks back at home and let them know that, hey, it's possible. If we're here, we're all Black, we're all from Africa, we can do it. And we are one of the best in our fields. You can equally do it. Just don't give up.
So I'm just laughing at your comment, but I wanted to remind you an African proverb: a prophet is not respected at home. I can tell you without prior relations in Kenya, it's always difficult to go to Kenya and have the same impact. But then I use my Professor Ndao, and my friend Dennis to do the work. So that connection is very, very important. Yeah. But we are running out of time here. But I just
want to add the small things on Edwin's stuff. I just want to say what he was saying is something that we keep discussing every day and try to find a solution. And I think one of the solutions that we can have is to teach a young student in Africa how even to apply in the United States. Yep. They don't even know. They will send an email with one sentence with the CV that whoever sees the CV will not hire you without knowing who you are. So having kind of a workshop in Africa that can be on Zoom online and teach them how to make a CV, what kind of email you should write, what kind of institution you should target, how you can get in the system. Again, as Edwin said, when you are young faculty, the competition is so high that you want to save your life first before starting to bring someone in the same. So, but those kind of baby steps, we can do it and prepare them. And when most of us become like associate professor, we are in the safe position, you can start bringing it. Because when you hire a student, you want to help African guy, but if you bring him, he doesn't have the knowledge, you need him 2 years to catch up. And you can have another guy that can do the work the day after. Mm-hmm. You will move for that to save yourself and after get back to that. But we can start with the very small stuff, teaching them how to write, teaching them how to present, teaching them how to talk to people, how to write an email. And from that, they will get in the system slowly. And from that, we can get them where we are today.
Yeah. And I think actually, if I can jump on that, Abdoulaye, I think when we look at the future of African science, there's a lot of talent, and with the information flow, people are getting way much more informed than during our generation. I have had the benefit of working with my alma mater in Kenya, Kenyatta University. And by the time I go there to teach for like a few days on intro to materials with colleagues from here, we find that the student knows so much about us before we even show up. They ask you questions about your work. The moment they see the flyer, they can go on Google and pull you up, and they can start asking you questions directly related to your work. And it was a big surprise. And so what also we have done, or I have been fortunate to get involved in, is we recruited some students from Kenya. And what surprised me is that those students now are running a forum, a Zoom forum every year. 3 young women that we picked from Kenya very early. They came to Iowa State, did their PhDs there. And now every year they run this online forum to train their peers on how to get applications, what kind of language they need to use. And the giving back is something that actually comes from African villages. And I think that's what we're struggling with. And I think we can delegate. We build mentors and we delegate to them. And then we benefit from people like Professor Ndao, who went for PhDs in China. It's not just US and England and Germany. We also have a huge population of African students going to study in China, in Malaysia, and even Dr. Karanja, you went to Finland and New Zealand. You know, before he went, I saw that you went to Finland. I had never known anyone who went to Finland for their PhD. So it's very interesting that we can share all this information across the divides. And we are running out of time here. So very quickly, Prof, I wanted to ask you to comment about where do you see the women, the African women scientists in the next 5-10 years? What role do you see the young women playing in shaping the narrative of African science?
Okay, thank you very much, Professor. And also thanks to the fellow panelists. They have really done it well. And we keep on enlightening each other. Allow me, first of all, to say that at Kenyatta University, we have the peer counselors. And when we take them through the training, we take them through personal branding, even writing the CVs and the like. However, the university also has a program known as the Glowing Leaders program, whereby all our finalist students are taken through a leadership training, and they are given a certificate at the end of it all. And in this leadership, they are taken through now how even to write CVs, how to write cover letters, how even to apply for interviews, how to attend the interviews, what is expected of them, apart from other things like what is leadership and the like. So that is something that we do. And I want to believe that our students are becoming better, and could be other universities can borrow from that. And coming back to the question Professor Martin has asked, as far as women are concerned, actually, we have a very, very bright future. I know the past has not been very good, but for now, the future is bright. Why? Because there are a lot of mentorship programs in place. If I may mention 2 of them, there is the Mawazo Institute that is running all over Africa. And this one is mentoring women. And apart from the mentorship, it is also giving them funds. I am a mentor in this program, and we are doing well. The first cohort has already graduated. I had 3 PhD students who I worked with, and it was good. And I also attended the graduation. Then we have another foundation that has just been put up by Professor Gila, and it is African Women and Youth Education, Science, Technology, and Innovation. Again, it is also another mentorship program that is coming, and I know it is going to go a long way. And also, like KU, we have had very many mentorship programs for even women in science and engineering. And we also have the UNESCO STEM Kenya that is targeting our women right from down there. Actually, last week, but one, I was in one school whereby girls from very many secondary schools are assembled, and we were taking them through this. And we were very many ladies from in STEM careers. We had architects, we had engineers, we had mathematicians, we had physicists. All the areas were covered. And you can imagine it was good. And we also benefit a lot, including even the marine blue economy. And so I must say that we are doing well. And in addition to that, there is a lot of funding now that is targeting women. The affirmative action is also coming on board, and we are happy with that. And so those are some of the things that I can see are pushing us ahead, and we are happy. As women, we are not yet there, but I want to believe that very soon we might even overtake you in quotes. Thank you.
Thank you very much. That's the dream. You know, that's what we want to think about. I think there's so much we can talk about uplifting the continent, and more importantly, rebranding the African science talent. And I want to thank all of you for coming up. I want to thank our speakers for an amazing time. And I will switch back to sharing my slides because I want to share with I want to share. Unfortunately, our one of our panelists was not able to join. She had to step out and go for an engagement. She's the constituency. She's in politics and dealing with her people at the constituency. So I wanted to mention that Abdoulaye, we will send this certificate to you virtually. We thank you very much for honoring our volume 151 at iCANX. And Abraham, I will also be sharing this certificate virtually, and we are very, very grateful for your talk. I want to remind everyone about next week. We'll be hosting the very talented Francesco Sterassi, who will be talking about a very unique kind of therapeutics. And please join us on Friday next week. And with that, I want to say thanks, everyone, and have a wonderful, wonderful day.
Thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最 造奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什